If okay, the thing's already recording. Okay, good morning, everyone, for this distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Mehdi Mirakhorli, Associate Professor of Software Engineering and Kodak Endowed Scholar, University of Hawaii in Manoa. Dr. Mehdi is an associate professor and his research interests on the intersection of software engineering, cybersecurity, and AI. Dr. Tarrit Mirakhorli has served as a PI on research and development awards and contracts of over nearly $21 million. He's an associate editor of IEEE Transactions Software Engineering and Empirical Software Engineering Journal. He is a recipient of NSF CAREER Award and multiple distinguished Best Paper Awards. Dr. Tarrit has supported the implementation of President Biden's executive order on improving the nation's cybersecurity, software bill of materials, and the U.S. government's vulnerability management strategies. Dr. Mehdi, is an extreme honor to have you as part of the webinar series at UND. Thank you so much for spending your time this morning with us. And the floor is yours. You have about 45 minutes or so to talk about what you have, and then we leave 10 minutes for Q&A. Thank you.
Hello, everyone, and thank you so much for having me here. It's a pleasure to be here and share the results of some of my work and have a discussion on a topic that I personally care a lot. Today, I wanted to talk about secure by design and by default and discuss what it means and what it takes for us to achieve secure by design. But before that, I wanted to start with the story from Greek mythology. It's the story of a guy named Orion. He was a giant. He was the son of sea god, and for that reason, he could walk on the waves. One day, he goes to the neighboring island. He drinks and he gets drunk and he makes troubles. As a punishment, the ruler of that island makes the Orion blind and threw him in the water. Orion manages to swim and go to the neighboring island where the Hephaestus, the smith god, had his forge. Hephaestus tells his servant that was named Sedalion to guide Orion to the east where the sun could heal his eyes. So Orion puts Sedalion on his shoulder, and Sedalion serves as his eyes so he could get to the east, and finally his eyesight could heal. Sedalion was known as someone that could see far, not because he had a good eyesight, because he was standing on the shoulder of the giants. And this statement, the standing on the shoulder of the giants, have been attributed all the way back to Isaac Newton, that said, if I've seen further, it's by standing on the shoulders of giants. And what it means that we use the understanding guided by major thinkers who came before us in order to make intellectual progress. But I wanted to know, the question I had is that on whose shoulder do we stand to solve software security crisis? Every day there are new vulnerabilities coming in the news. In last 10 years, if you look at it, Heartbleed in OpenSSL, Log4j, and we have either ransomware attack or software vulnerabilities every day in the news. And I'm not talking about modern vulnerabilities that we are going to see with the AI software, just traditional software. We've been facing growing number of vulnerabilities. How can we solve software security crisis? I start looking around and see on whose shoulder we stand in solving software security crisis. What are the areas that we could learn from other practices, best practices that we had in software engineering? This is a news article in April 10, 1981 from New York Times that talks about a space shuttle that says space shuttle will be ruled by majority vote, not the votes of astronauts, but and or crews, but the computers that sit on space shuttle. And I think some of these historical software are good examples of how we achieved certain qualities. If you look at, for instance, a space shuttle, I was recently looking at it at NASA website that was saying shuttle computers navigated record of reliabilities. These are general purpose computers that manage to operate without failure for a long period of time. And similarly, there are other application domains that we have seen very high reliability, dependability. For instance, in medical device systems, we have seen that um, growingly we have improved the safety of these medical devices. But we have a lot to learn from these application domain that are certified and regulated. If you look at avionics systems, you don't see on every day and news that airplanes, flight control software are crashing because of software defect. It has happened, but it's not as often. Um, we have done a lot better in safety critical systems versus secure software. I know President Biden's executive order, NIST, tried to define what is a critical software. But if we want to, in my opinion, if we want to succeed in securing software, we need to go back and learn from those lessons that we had in building safety critical avionic and regulated software. General purpose software today, SaaS products, or critical software today are not regulated as much. On whose shoulder do we stand in solving software security crisis? I want to discuss some of my work in software security that leverage lessons learned from regulated, certified, and transparent domain to enhance software security. There have been many studies around cost of identifying and correcting defects. This is an article from 1997 by NASA that demonstrated that the number of hours that takes to find and fix defects in early software development phases are significantly less than later software development phases. For instance, by doing formal inspection of requirements or design, it may take us 0.7 hours to detect and fix issues versus by testing, it might be 5 to 18 hours. And this is a concept that now we hear a lot. Shift left means shifting our software assurance activities to the left side of development cycle. Instead of focusing on post-deployment, doing so much testing, chasing defects, we should start software assurance activities early on in the software development lifecycle. We did shift left in 1997 to address software reliability, and there's a lot to learn from those practices. And it's coming today again, there are articles that talk about cost of identifying and correcting security defects in 2023. It would take approximately $14,000 to find and fix a security bug at production time or post-release time. And that expense is allocated to penetration testing of application, paying bug bounty program to find vulnerabilities, using DAST, SAST, and fuzz testing, dynamic static analysis tools, performing code reviews, um, having firefighting that the application is deployed. Now we have to see how we can patch it in the next few days without being exploited by adversaries, mitigating the downtimes of the facilities. These are all expenses that we have to pay once we focus our assurance activities post-release. And studies shows that this expense will be significantly less, at least half, if we shift it to the left at the acceptance testing time, integration time, or during the coding with code reviews and other techniques. And it would be significantly less if it's focused during the design time and approximately $139 hours to $139 to find or fix one of these vulnerabilities. And that $139 is practically an hour of a mid-level designer to review designs and potentially find weaknesses in the design. So with this mindset of shift left, um, Secure by Design aims to shift the main focus of software assurance activities from finding security bugs, chasing security bugs, to identifying flaws and weaknesses in the design in early phases. But there are many definitions of Secure by Design. Here I want to provide a working definition of software design and Secure by Design. Let's look at an example. This is the architecture of the design of Apache Hadoop. It's a parallel computing platform. You see a bunch of components, job tracker, task tracker, name node, databases, and different instances nodes. It uses a master-slave architectural style that the master process is responsible for monitoring the performance of each of the replicated processes. Every element that you see in this diagram has a purpose. Those purposes are requirements, software requirements, why we built the system, why do we care about certain quality aspect of it. For instance, in Hadoop, the stakeholders, the user communities wanted to have a highly available system where hardware failure can be the norm rather than exception, and still the system would function. To achieve that highly availability requirements, designers decided to have master-slave architecture style where the slave processes are replicated, checkpointing to synchronize between the replicated processes, using heartbeat architectural solution to detect the failure of any replicated processes. When a process was replicated, every few seconds they were sending a heartbeat message indicating that they are alive, they are alive. Therefore, the system could um, identify if those components are running or have crashed. And other architectural decisions, such as using proxies to make sure that the failure of one of the underlying task trackers or data nodes are shielded from the clients, and the clients would never notice a part of the system has crashed. Other requirements provide secure services for the client. To achieve that security requirements, the designer of the system decided to have mutual authentication with Kerberos on RPC connection, maintaining an audit trail of all activities in the system, encrypting the data on RPC, encrypting the data transfer and encryption on HTTP, and also other decisions such as secure data node where the data nodes must authenticate themselves. If we look at any non-trivial system, it's likely to be composed of hundreds, if not thousands, of such architectural design decisions. So what is secure by design? It's a collection of such design decisions that we make, designers make, in order to address quality attributes, security, privacy, resiliency. Where do we get these ingredients, design decisions that I mentioned? We have a wide range of security tactics, controls, or patterns that we choose them to increase the security of systems. These are designed to address concerns such as detecting attack, resisting attack, preventing attack, reacting to attack, recovering, but also making security a default feature. You might be familiar with many of these concepts, but in different names, perhaps security controls or patterns. For instance, sanity checking, exception detection, authorizing users, managing user sessions, encrypting the data, performing audit trail of activities. So Secured by Design becomes a collection of such design tactics that we use to enhance the security of the system. In Secure by Design, the architecture is the main step to secure the system. And it starts by identifying misuses, abuse cases in the system, performing threat modeling, and making appropriate design decisions among these architectural tactics to mitigate the threats. If we look at design in general, what we've learned is that when we make design decisions in highly available, highly dependable systems, avionics system that I use as an example that we could learn a lot from. There are a lot of concepts there. We have patterns and anti-patterns and common mistakes that designers make. But when we started this study, we learned that there was not many concept around common design weaknesses that have vulnerability consequences. There was a lot of things about insecure coding, but not about design weaknesses. So we started investigating how can we come up with a list of common design weaknesses. If you look at here on the examples that I have, that my former PhD student, Joanna Santos, that is a faculty at Notre Dame University now, started that work. On the left side, I have an incorrect typecasting. That is a coding problem, security coding problem. On the right side of that diagram, I have a design flaw. In this design flaw, the designers decided to secure the system by using authentication, but they place the authentication logic on the client side of the application. So the authentication logic sits on the user's machine, sits on the adversary's machine. Adversaries can bypass the authentication. Client-side authentication is a flaw, it's not a defect, it's deeper and is not in the code, is on how the software is designed. We wanted to come up with this, develop a catalog of common design weaknesses. We decided to learn from real software vulnerabilities that were disclosed. We studied over 20 vulnerable systems. We looked at National Vulnerability Database. That's a database maintained by US government, Homeland Security, and NIST that keeps track of all vulnerabilities that are disclosed publicly. We also looked at other resources such as MITRE, Common Weakness Enumeration collections. After review of real vulnerabilities, we applied a very detailed coding practice that we coded each vulnerability reports. This is a CV, for instance. You see that is a real vulnerability reported in a system, identifying the root cause of those vulnerabilities. Then we tag them if they're coding or a design related, if they're design related, how they happened, why they happened. As a result of this study, we built a catalog of 224 security issues rooted in the software architecture and software design of applications. These common design weaknesses that have security consequences either could be omission, commission, or realization flaws. And this concept, we take it from risk management concept. Omission means that designers miss to make an appropriate design decision. They just forgot a concern altogether. For instance, password were stored in a file without encryption, while the system leverages authentication using password. Designers forgot to store password with encryption. That's an omission. Decisions that were never made. Commission flaws are the type of flaws that designers come up with a creative way to design the system, but that is a poor design decision. It is incorrect, such as client-side authentication, that there is a design decision, but the authentication logic is on the client side and therefore can be bypassed. Realization flaws are the type of design decisions that at the design level, the concept is correct and is appropriate. But when programmers implement them, they implement them incorrectly. For instance, the system has the logic of authenticity, but the way it is implemented in the code is correct, and therefore there is an authentication bypass. These 224 security issues, we categorize them into three classes of design weaknesses. Then we wanted to we established this catalog, and later on this was adopted by Maitre. If you look at architectural concept catalog in Maitre CWE website, you'll see all the architectural concept that we have. These are security tactics that I showed you early on, and if you click each of those, they would demonstrate more fine-grained flaws, design flaws, either omission, commission, or realization flaws associated to each of these security tactics. So basically, as a designer, if you know your application has any of these security tactics, then you can come to this catalog and see what are the common ways that these tactics could fail, either through omission, commission, or realization mistakes. Once we established this catalog, Mitra adopted it. We wanted to know how common are these common architectural weakness enumerations. We call them CAWs. We studied several systems. We extracted the vulnerabilities that were reported in these systems. We reverse engineered their architecture. We mapped the vulnerabilities to their code and architectural decisions that were made. And the system that we chose were Chromium, Thunderbird, and PHP. These were some of the top vulnerable systems. Our study showed that 42% of vulnerabilities in Chromium had a design root cause. And in PHP and Thunderbird, that was around 38%. And a lot of vulnerabilities that we studied that had a design root cause were either related to validating the inputs that the user or adversaries were providing to the software, or related to the tactic, authorized actors security tactic. Those applications that we studied were more of a web-based application. We wanted to look at other application domains and see how these vulnerabilities, design vulnerabilities, appear there. So we chose industrial control system as an application domain. We built a reference architecture for industrial control systems. Here's a view of that. We have PLCs, programmable logic controllers, and remote terminals. These are devices that work with the equipments in the field and manage their operations. We have a human machine interface that configures the plants, troubleshoots it, and that's the interface that users work with an industrial control facility. SCADA that controls PLCs and RTUs, data historian that keeps log of daily operations in a facility. So we built this reference architecture. Then we went and looked at vulnerabilities that were reported by vendors in security advisories. And we looked at the root cause of these vulnerabilities. Basically, we found CWEs, how this happened. We mapped these vulnerabilities to our catalog of design vulnerabilities. And this study basically showed that out of all design weaknesses, human-machine interface component of industrial control system had the highest percentage of design-related vulnerabilities, then SCADA, then PLCs. And the reason for that was that modern industrial control systems use a web-based HMI, and therefore they borrow and inherit all the vulnerabilities that are common in web applications. Overall, in industrial control systems, 62% of security advisories that we studied mapped to at least one common design weaknesses. And similarly, top security tactics impacted were validate input, authenticate actors, authorize actors, and encryptions. We realize that these design vulnerabilities are very common, and I mentioned that we want by shift left, secure by design, we want to shift security to the left, software assurance activities to the left side of the software development lifecycle. But what it takes to achieve a secure by design? Again, I want to go back to the domain that we really did well, especially in safety critical system, avionics system that were regulated. We have a lot to learn from 30 years worth of methods, models, tools, and approaches that focused on early assessment of software requirements um, in those domains where this and in requirements, we really think of what do we want to build, how do we want to build, what are the specifications that we give to the developers to build the software. There have been a rich set of methods and techniques. For instance, in many safety critical systems, we have safety cases. That by safety cases, we analyze the software system, we identify how they could fail and what are the mitigation techniques. So it enables us early in the development life cycle, think about all the possible failures, model them, and come up with mitigation techniques. And this has been used in many defense systems, medical applications, critical applications, and have been shown very effective in uh, making sure that the system that we build are secure. We typically use them in a regulated domain. For instance, if you build a medical device, pacemaker, insulin pump, you often have to go through FDA regulations. They review such artifacts, safety cases to make sure that you've gone through best practices. You have a high hygiene in terms of building software applications, and you've identified majority of safety cases that demonstrate how the software may fail, how you deal with it. In security domain, we have similar concept. For instance, we have use cases and app use cases. This is a use case diagram for those that are not familiar. Basically, it's a way of modeling the users, how they interact with the software, and what features of the software do they invoke. That's the left side, those white diagram. And on the right side, we have abuse cases. Once we do use case modeling, we focus on how the system can be used. And if we do have use case modeling or misuse case modeling, we want to enumerate ways that adversaries, unauthorized users can abuse the system. Similar to safety case analysis, this is a best practice. If we leverage it, it would help us to enumerate ways that software systems can be abused. We cannot have secure by design if we are not thinking it from the beginning, from the requirements analysis, early phases of a software development lifecycle. This is a work that a group of my students and I, within a sponsor, we focused on automating generation of misuse and abuse cases. And we developed an approach that looked at requirements and specifications often written in text. It performed requirement synthesis, identified abuse, misuse cases, and performed reasoning. The underlying engine in this approach was a natural language processing technique and a formal reasoning technique that formally modeled the entire design weaknesses that I early on mentioned to you, the catalog that I showed you. We formally modeled that catalog in Alloy formal reasoning language. Then we use natural language techniques to instantiate the models that we had. Then we could do reasoning over a natural language documents to identify misuses, abuse cases, and generate an attack theory. And much of that, this is pre-LLM large language models that we basically did part of a speech tagging and etc. to be able to generate those misuse and abuse cases. When we think about secure by design, we need to start from requirements. We need to be able to perform software requirements analysis, analyze the feature of the software, and enumerate all the ways that the software can be abused. Once we identify those, we can then rethink what mitigation strategies should be used to mitigate those abuse and misuse cases. Obviously, threat modeling is another concept that needs to be employed when we do secure by design. A lot of time we get individuals working on these tasks, such as requirements analysis, that are not security experts. So there is an educational gap there, but also there is a gap in terms of tooling that we need to use. The reason that we automate this process is that the sponsor that we worked with, they often dealt with software requirements documents that were hundreds of pages, thousands of statements about what is the software, how it needs to function. And manually reviewing those will be very, very difficult. And often those requirements may have security requirements or may not have security requirements. That took us to the next project, where we realized that sometimes security requirements are missing. Then we start building an application that the main goal of this application or tool was to look at a software that we are building, to look at the set of requirements for that software that we are building, and tell a requirements analyst, someone that analyzes these requirements, write these requirements, what security requirements he or she needs to incorporate in order to make that system secure. We relied on using GAN models. We fed a description of a system that we were building in that GAN model and for an application that we were building. We fed those requirements to the GAN model, and we asked the GAN to synthesize security requirements for that application. So the GAN had access to functional requirements, feature of the software, and it was supposed to synthesize security requirements for us. And in the GAN model, basically, we had two components, one generator, discriminator. Generators tried to synthesize requirements. Discriminator tried to say if these requirements are generated by a machine or are generated by human. They competed till they got to a balance point, and the GAN managed to generate security requirements. In this table that you see here on the left side, we use the application court case management software that didn't have, it had some security requirements. We removed these security requirements from the data set to see if the GAN could actually generate realistic security requirements. So on the left side, you see the original security requirements of that system that we removed them from the data set, and we ask the GAN model, can you tell us how we could make this system secure by generating a set of requirements for us? And on the right side, the GAN generated security requirements. The highlight shows if those requirements were matching, and we realized that we could generate very realistic security requirements using GAN models. And again, this was pre-LLM. We had some brief testing with LLMs as well. And this approach, I think, in anecdotal base, we believe was generating better results. But even if we did security requirements on all those, we made sure we have enough security requirements from the beginning. We analyzed misuse abuse cases, we identified those, we did threat modeling. Now we need to come up with a set of design decisions to make sure that the system is secure and resilient against the attack. So the design phase itself becomes important. Requirements are pre-design phases. And in design phases, again, we have a lot to learn from software architecture first approach to resiliency, where Department of Defense, NASA, avionics systems have accumulated so much knowledge in terms of how do we design dependable system, how do we design a resilient system. We came up in order to better reason about security of risk system at the design time. We came up with the concept of security assurances. Basically, we learn from safety critical systems that we often have assurance cases. And we develop assurance cases for the secure by design claim. I'm going to show you how the assurance cases would look like. Here is the design of a satellite system in a modeling language. It's OSATE. It's a modeling language that Department of Defense often use for modeling the architecture of the applications, showing components, processes, threads, relationship between them. What is assurance case? Basically, in assurance case, we have a set of claim in the system and we want to see based on how the system is designed, if those claims are satisfied or not. It's often was used for either safety, dependability, reliability, quality attribute, but we started designing assurance cases for security. For instance, one instance of assurance case is input validation. We wanted to make sure the system has at least one validator in its design, and there is at least one target, which is a component that performs security critical operations. Then we have a top claim that invokes a set of subclaims that target components only receive external data from outside trust boundary if it is validated. So basically, this assurance case says for a system to be secure, you need to have target components that perform security operation. You need to have an input validator, and any data that comes from outside the trust boundary needs to go through that input validator. We developed these assurance cases in a language that is called Resolute, and that's a language for performing software assurance cases. It's a reachability language that allows us formal reasoning, but also reachability language that also allows us to see claims and subclaims that we make if they're satisfied or not. So we came up with the large number of assurance cases like this. These are design level assurance cases. We built it off of the common catalog of security weaknesses that we had developed. If these assurance cases were maintained, we knew that we don't have those design weaknesses in the design of our application. We applied it to these avionics systems. We found that many design weaknesses could be detected using assurance cases. The way it was applied, I'm not going to go into details. We built those assurance case models. We use AI machine learning techniques to annotate design models in automated way with the elements of our assurance cases. Then we performed the analysis. Using this analysis, for instance, we could find if an application had any design flaws. If you remember, there was a drone that was the target of cyber attack that was forced to landing. With our analysis on this DARPA project, we found that we could actually have detected the design weaknesses in the architectural design of that drone application. But even if we design the system, we did requirements analysis, we designed the system, we perform formal design modeling or informal design analysis, still we need to we do not achieve the full benefit of secure by design because of the realization flaws that I mentioned early on. Now, even if the design is correct, the implementation is important. We want to make sure the implementation follows those design. So if you look at this software change cycle in ideal world, we have the environment, we have the source code, we have is-a architecture and intended architecture. Intended architecture is the design that we had in our head. That's what we thought about we want to have. Is-a architecture is the architecture in the source code. In ideal world, every time we change the code, a request comes in, we look at the architecture, we see the impact of the impact of the change on the architecture, we modify the is-a and intended architecture together, so there is an alignment between what we had on the paper and what is implemented in the code. However, in real world, it's a little messier. A lot of time when we change the software, we directly go to the code. We have firefighting situations. We quickly change the code. We may not pay attention on the impact of that change on this architecture of the system, the overall design of the system. And therefore, what happens, there is a drift between is-a architecture, the architecture that is captured in the code, and what we had in our mind as our intended architecture, or what was documented in the model, in the papers, on our whiteboard as the architecture of the software. That drift results in degradation of the architecture. Now, that secure by design that we had in mind may not exist in the code anymore because the code does not really match the actual architecture of the system. A lot of time there is a drift and we end up with a design that is significantly different than the architecture of the system. This is the architecture of Hadoop on the paper, how it looked like intended architecture. This is the implemented architecture of Hadoop that looks like a big ball of mud. The nodes in these diagrams are Java files, the dependencies, the edges are dependencies between Java files. All files and classes in Hadoops are interconnected. It doesn't look like a big ball of mud because I showed it in circle. This is reverse engineered architecture. It looks like this because there is no boundaries. The programmers made method calls everywhere that they need to or they wanted. And over years, the Hadoop architecture turned out to be this mess. What we did, we wanted to see how we got from that beautiful architecture to that ugly one and what is the impact of that, why the software degrades. So we started building a matrix in Hadoop system, but a number of other open source systems that showed the developers' contribution to different design fragments of the system, different security tactics such as authentication, authorization, role-based access control, Kerberos authentication, policy-based access control, and so on. This matrix shows the programmers and which security controls they did work on, and how much commits they have and who owned that part of the code. Based on this matrix, we developed a persona model for these developers. Basically, you see a persona here that says their name, their roles, responsibilities. Then we spied on these developers. We went on LinkedIn, social media, all their activities in open source world, and anything that they had online. We created this profile for them that showed what are their skills. And those inferences were made by using machine learning, classification technique, classifying the commits that they had, content that they had created, looking at their profile and deciding if they are security savvy, architecture savvy, they know software design or not, and what are the skill set that they have. After we generated these personas for every programmer in those open source systems, we classified them into architecture savvy and non-architecture savvy models. Then we looked at who contributed to the defects in these security fragments of the system. The results showed that non-architecture savvy developers tend to introduce more bugs in the design fragment of the system, and the design fragments that are owned by those architecture savvy developers are less likely to have bugs. And we did interviews of these developers, and some topics that came out that in open source project, you cannot really dictate architectural decisions. It's all about persuasions and communicating. And a lot of time they deal with firefighting situations, Hadoop crashes in a US bank or Facebook, and they have half an hour to fix those things. Other topics that came up, but you couldn't really test these design decisions. We have software testing, but it's about the feature of the software rather than such design decisions. That gave us the idea of building a plugin that could bring design thinking into developers' coding activities as they write code. They could understand the security implication of their code. We could visualize the security concepts behind the code that they are kept informed of security implications of the code that they write. These are all pre-LLMs, and I'm sure with LLMs, we can actually even do more in terms of bringing design thinking into developers' coding activities, if we happen to code in future. I'm not going to get into details of this technique. It was a classification technique that classified code into different security concepts. And then we used visualization technique to visualize those security concepts. Another concept that I wanted to briefly talk about that is important during the software design is attack surfaces. It refers to the critical points on the boundary of software that is accessible from outside. It is not very well understood. When we design a system, one of the major goals of Secure by Design is to reduce software attack surfaces. It means ways that adversaries can interact with the software. Unfortunately, in the literature, there is not much concrete information on what are typical software attack surfaces. To address that, we apply the grounded theory, which is social science techniques, on real vulnerabilities to see what are real attack surfaces that we have seen in exploited vulnerabilities. We coded these and we came up with 3 components of attack surfaces: entry points, where the adversaries interact with the software; target, where do they want to reach to exploit the vulnerability; mechanism, how do they reach to that point, the avenues that they leverage to connect entry points to target. By analyzing thousands of vulnerabilities, we came up with large catalogs that enumerated all the entry points in the software that can be abused, all the target components that adversaries want to reach out, and mechanism that they often abuse to reach to those targets. We made a comparison between these detailed components of attack surfaces that characterize software attack surfaces with what we knew in the literature. This study found 254 new concrete components that did not exist before. A small percentage of code level entry points were covered in the literature, and what we knew to that date about software attack surfaces, instances of attack surfaces at the code level, was 6% of what we discovered in this study. Even if we understood what the software attack surfaces are and we managed to build tools to measure that for us, help us to reduce it, we are going to deal with another problem if we really want to achieve Secure by Design, and that's software supply chain. Software supply chain means if we build the software, what are the ingredients of the software? If you go to a grocery store, you buy a product, you have a barcode that says what you're buying. For software today, we do not have that barcode. We don't know what dependencies, libraries are we shipping into this product, and that can cause lack of transparency. Software can be bloated with lots of vulnerabilities, and consumers have no idea what they're purchasing. President Biden's executive order partially focuses on this concept. that we want to build software bill of materials, a barcode that tells us what is in that software. We did a landscape of study. We looked at over 100 tools that in last 2 years have been developed to support President Biden's executive order in terms of generating software bill of material, consuming software bill of materials. We demoed around 80 tools, and we found the emerging use cases in these software bill of materials and software supply chain tools. There are a lot of new use cases about SBoM generation, converting a SBoM, merging a SBoM, signing a notary of this SBoM. If we have that barcode, we can do a notary that the consumer knows that it came from us. Use cases are growing around quality check. Are we generating the right SBoM? What is the authenticity of it? A lot of use cases are emerging around software supply chain vulnerability management, detecting dependency misuses. The SEAL programmer can abuse, misuse dependencies in a way that impacts the quality of our SBoM, and information sharing across supply chain. In this study, we looked at a large number of tools. We ran them on the same projects to see if different SBoM tools would actually give us the same outcome or not. They would highlight the same software supply chain risks or not. And we realized that actually there's so much inconsistencies and interoperability issues between the tools. A lot of time tools are missing components, they miss vendor information, sometimes they capture direct dependencies, but they don't capture transient dependencies within the dependencies that they found. And your software supply chain is as secure as the tool that you're using. And it's really tool dependent as of today. And that highlights a lot of opportunities to improve the quality and interoperability of existing software supply chain tools. What I wanted to mention today was that we have a lot to learn from regulated, certified domains that we manage reasonably to succeed in those domains, and there are best practices that we could apply. Today, I highlighted some of the ideas that how I leverage those best practices and learn from resilient software, dependable software, and took those best practices to apply to secure software development. That concludes my talk. I'll be happy to answer any questions.
Thank you, Dr. Mehdi, for a very fascinating conversation talk. I think you give a very big picture of the software assurance area. And I think you touched several things during your talk, ranging from architecture flaws to even LLMs. But Jameson, we can start taking questions. Maybe I'll start with the first question. I think, so, in your last slide, you talked about SBoM, right? Do you see, you did say that aviation and medicine fields have very certified and regulated framework. We have a lot to learn from. And, do you see this SBoM as one form of quality check? If so, how do we make sure that people, we can be able to validate this and maybe, adapt to, in a larger scale? Where are we? What do we need to do to go from, the lessons learned from aviation networks, softwares to energy or manufacturing or, whatever the other applications domains are there? I know it's kind of a very loaded question where you can't find any consensus, but I want to, where do you see the future of this area as you plan to work on?
So it's a very interesting question, and there are contradicting answers, at least among the practitioners and research community as well. So what government practically is doing is leveraging the buying power of the government to force industry to adapt software supply chain. So what executive order says, if you sell a software to the government, you need to tell the government what is your supply chain, what is your SBoM, and what are vulnerabilities in that SBoM, basically dependencies that are vulnerable. Initially, everyone thought that, okay, not everyone works with the government. There's some companies sell this, so that's it. Those companies needs to follow that procurement process. But then it came out that, well, actually, companies are selling cars to the government. Now, automobile industry needs to generate SBoM and provide SBoM to the government. And there are so many other vendors that directly or indirectly work with the government. So it's a creative way to change the industry. However, in the software security domain, we have that practice of doing things that are expensive, exhaustive, and has not changed the hygiene of software. For instance, we built static dynamic analysis tools. Companies extensively use them. They had teams that had to review so many defects and vulnerability reports. Still, the software is not secure today. That concern resonate with the SBoM world today as well. So SBoM world fixes a small piece of the puzzle, and there's a lot of issues that are coming out even with that. So it fixes the issue of transparency and known vulnerabilities. It would just help us track which known vulnerabilities do we have in our software. But there are many broken pieces. For instance, today we don't have any form of software identification. If you buy a car, you have a VIN ID. You can know what is your car. You can have a recall and etc. But today we don't have a way of accurately identifying a piece of code. There have been discussion about different forms of software identification, suites, CPEs, Perl, which is package URL. So that's one broken piece. How can we accurately identify a piece of software? And if we can't do that, we cannot really generate an SBoM. There are a lot of issues around vulnerability management that we need to be able to map software vulnerabilities to SBoM elements. There are tools that needs to be improved in terms of being able to analyze source code, generate SBoM, being able to analyze binary code, generate SBoM. But then there's so many package management systems that we are using today to build our software, and these tools need to be able to accurately generate SBoM by leveraging those package management. I think a bigger problem, in my opinion, and I've done some real testing. I think it's gonna be really complex artifact. If you look at the software, medium-sized software, you might have thousands of dependencies there. And those 1,000 direct dependencies, each of them may have another 1,000 indirect dependencies, transient dependencies. So if you cover transient dependencies in your SBoM, you're gonna be left with thousands of dependencies that your SBoM captures. And guess what? Each of these dependencies are gonna have a large number of known vulnerabilities. Now, as a vendor that I sell my software to government and I want to tell, this is my SBoM, these are all vulnerabilities that come with my product, they are gonna be overloaded with a large number of vulnerabilities. So that's where triage become important. How can we look at such a landscape, improve productivity of developers that they could identify among the thousands of dependencies, thousands of vulnerabilities, which one are actually exploitable, which one does not impact their product. So tools fidelity is gonna be very important. Otherwise, we would, similar to static analysis tools, we are gonna end up with the techniques that exhaust developer. We put a lot of resources, but we don't have tangible ways to ensure software security is improving.
Thank you for that detailed explanation. And I have one follow-up question on, you mentioned that yes, we need more. There's a lack of software assurance tools. In one of your methods, you talked about, you started by having one validated, having one target. When one target meaning mapping those critical secure operations. And how do you elicit that requirement? Sometimes it's not straightforward in having that secure critical operations. And I'm just curious to put your thought process on this. Do you, in your work, took what that critical secure operation is, or do you have to do that homework to figure out what the critical operation is, and then elicit that, and then do this, approach, and I don't know, I'm just curious to see, or do we have to go with hybrid approach?
I think this is a very good question, and this was a DARPA assurance program that we were part of it, and I think, in my opinion, in some of those systems, and we discussed this as well, everything was a critical component. Um, so that's one way of looking at it, and there are techniques that have looked at it, and we actually struggled with this a little bit. So one approach is that, I mean, if it's a defense software, if it's a drone flying, everything could be a critical component. And that's where the concept of taint analysis comes. You have an input coming to the system, it goes everywhere, different places in the software. You do taint propagation to see which part of the software would be impacted. And if you have a sink or a dangerous operation in that part of the software, right? So we took different approaches for it. One thing that we tried to do is um, to annotate lots of data and use machine learning to tell us what is a critical component. So that's one way of it, relying on machine learning to tell you what is a critical component. In another work that actually we did for another agency, we looked at sensitive information. Now actually we are using GPT for it. We define different instances of sensitive information. We prompt to GPT. It analyzes our software and says, social security is a sensitive information, bank is a sensitive information, a directory address in a program is a sensitive information. So we work with GPT to be able to go beyond what we can enumerate. It has worked reasonably fine. In defense application, mm, we did that annotation part, but we also considered that any function could be sensitive. So it's a difficult um, concept, and it's similar to assets, right? You have assets in a software, how critical they are. We use the hybrid approach of either manually deciding in the beginning, then annotating models. If you build several avionics, let's say drone systems, you knew what is in critical in one of them. For any new drone, a machine learning techniques could tell you, yes, this component GPS um, is sensitive, this GPS component.
Thank you. I think I'm just looking at the questions and the time, but I think maybe I'll pull up. I'm not sure this is how does a developer go from being a non-architecture savvy to architecture savvy? But I think your point of that method or the paper that you talked about was, you know, to show, to comparison of, reliability from architecture savvy point. I mean, I'll let you answer that question. How do you see that?
I think there are different ways. Definitely education is a big part of it. Even today, I think there's a lot of discussions on software developers education, even folks that are already in the industry. We talked about workforce, we talked about the students, but now with the secure software, we are getting to the point that actually developers that are in the market, they're working, building things, we need to educate them, enhance their skills in some of these concepts and techniques. So there are two parts. One is education. The other piece is actually exposure to the concept. I gave this talk in a company, relatively large company in the state, and they told me we already have this profile that you created for everyone that we hire. And what we are interested to balance the team expertise. They said in their company, they assume if you work with someone that is architecture savvy, more likely you are gonna become architecture savvy as well because you are in the same team. But if you were in a team that no one was architecture savvy, it's more likely that you're not gonna also gain that experience. So the team structure was another concept that came out that it could improve exposure of developers to those concepts. But in short, I think it's education, but also today I think I would see new technologies would come out using LLMs, and we saw Microsoft spin out products for security, helping developers with security concept that kind of makes novices experts, or facilitates the transition from being a novice to an expert. I think it could be tools that you work with day to day, and it kind of gives you feedback. You learn about different design choices, consequences of that, mitigation of those. Um, I think that would augment the education part of it.
Good. Thank you. I think we're going to wrap the webinar because we're running out of time, and I think we'll have your email shared in case people have more questions, they can contact you. Thank you so much, Dr. Mehdi, for your time. I think you will receive a nice plaque from UND, and also a certificate signed by our dean. Thank you so much for your time and contributing to this webinar. We'll also send you the access to the recorded link, so which should also be used to promote, or for your own sharing. Thank you.
Thanks for having me. It was a pleasure, and I'll be in touch.
Yeah, we'll be in touch. Thanks.
Thanks.